Hi, I am Varun Joshi and welcome to day 21 of our Certified Kubernetes Administrator 2025 course. In today's lecture, we will explore multi-container pods, why we use them, and key patterns like init, sidecar, ambassador, and adapter. You will understand how containers collaborate inside a pod to build powerful production-ready apps. What I have on my screen is a diagram that you are already familiar with. Here I start with a single container, that is where we started our journey with Docker. Then throughout the Kubernetes lectures, we have been working with a single container inside a pod, and that container has typically been Nginx for us. And then at the very bottom, you see that we have a pod that has multiple containers. So we discussed this initially itself, that a pod can have multiple containers. In today's lecture, we are going to zoom in into the patterns you will see often used in production applications. Here, what is mentioned is pod can have multiple containers which mainly share networking. And when I say networking, what I mean is network namespaces. Now, what is a network namespace? Network namespace is firstly a Linux concept. It is not something that was invented for Kubernetes. How Kubernetes works is whenever you create a pod, a network namespace is created for the pod. And if that pod has multiple containers, all those containers share that network namespace. Now, what is a network namespace? A network namespace essentially isolates networking for the pod. So the routing tables, the IP address, the ports, and all these things fall under the network namespace. Since the containers inside a pod share the namespace, they can access each other on localhost itself. In this example, if container 2 wants to access Nginx, then container 2 can just write localhost port 80, and container 2 can have the Nginx's home page displayed. Another thing is, if container 1 is listening on, let's say, port 80, then you cannot have any other container listen on port 80, because as I said, the underlying networking is shared and ports are also part of that. So if container 1 is listening on port 80, then any other container part of that pod cannot have the same port. That's understandable. Now, second point is they also share storage. But here is the caveat. When you assign storage, you first assign it to a pod. Now, what difference does it make? The key thing is you can assign storage to a pod, and the containers on which you mount that volume can see the same volume. For example, I might choose to not map this volume onto container 2. If I don't do that, then container 2 will not see that volume. But if I choose to mount this volume onto both of these containers, then essentially they are sharing storage. So in this example, let's say we have container 1 as Nginx and container 2 as log collector. What will logically happen is I will map this volume onto both of these containers. But I'll do one tweak here. What I will do is, for container 1, I will give container 1 rights to both, let's say, to read and write data on this volume. But container 2, since this is just collecting the logs, I will only allow this to perform reads onto this volume, because this is just collecting logs. So these are the scenarios you can work with. One container can have minimal writes, another container can have full writes, or all the containers can have the same right. So there are various permutations and combinations that you can think of. So why use multi-container pods? Decoupling and ensuring requirements of main container is met. Main container, we are hearing this term for the very first time. So whenever you have this multi-container patterns, then there is one container that is your main container, your primary container. What is a main container? Main container is the container that runs your application logic. That is the main application. So if I talk about this example, then container 1, which is Nginx, is my main application. Container 2 is just collecting logs. Now in multi-container pods, if one is the main container, then what are the others called? They are called helper containers. So container 2 here is a helper container because container 2 in itself is not running the application. It is just helping the application that is running in container 1 to function properly, to collect logs for this application in this example. So here I'm saying decoupling. So what is decoupling? There is the core logic of the application, and there are things like authentication, authorization, log collection, monitoring, and I don't want to burden my application doing all these things. So what I do is I decouple all these external things into a separate container, and that separate container is called a helper container. Here I did not want my Nginx container to worry about collecting the logs and then sending those logs to somewhere else, maybe to a central repository. I did not want that. So what I did was I created a container 2 and told container 2, your job is to collect the logs from my main container and deliver it somewhere. And that somewhere would probably be your central logging repository, maybe an S3 bucket on Amazon. And I'll now scroll down. This screen has a lot of text, so do not worry about that. We'll see each component bit by bit. Okay, so at the top you see pod with 2 containers. We have seen that. Container 1 is the main or the primary container, and then there is a container 2 which acts as helper. We just learned that. Now there are different patterns you can have for helper container. The first pattern I want to discuss is init containers, also called initialization containers. When you hear the word initialization, you know that is the first thing that happens. So init containers are self-explanatory. They run to completion. What do you mean by that? They either are successful or they fail. If they are successful, only then your main container starts. If init container fails, then your main container will never start. As the name suggests, initialization. If initialization fails for something, then you don't proceed to the next step. And that's similar to what happens in Kubernetes. If init container fails, then the main container never starts. They run sequentially. Sequentially, can you have multiple init containers? Yes, you can have multiple init containers, and they run in sequence. If you have defined 3 init containers, then first init container 1, then 2, then 3. And only then, when all these 3 init containers succeed, your main application will start. Now let's see some use cases. First is DB readiness. I do not want my application to keep trying to access the database when database is not up. If I talk about a deployment that happens as a whole, then let's say you're deploying everything using Terraform and Ansible. You do not want your application to try to connect to the database if the database is not yet created. And init containers help you with that. They can check whether the database is up or not. And only when the database is up and init container confirms that, only then your primary container starts. Second is API health check. I might not want my application to start until and unless a specific API is available. And this is something we are going to test in the demo as well. Third is file or directory creation sync. What is that? You remember I told you that I can choose to mount this storage onto all the containers in my pod. if I choose to mount this storage onto my init container as well, then what my init container can do is, maybe I have a dependency, maybe my application has a dependency onto a certain GitHub repository, and I might want to clone that repository before my application starts. So init containers can be used for that. Since the storage is shared, init container will clone the repository, and once the repository is cloned, the main application will start and can use that repository. Fourth is service availability. This is also we are going to see in demo. Maybe I do not want my main application containers to start until a cluster IP service is created in my Kubernetes cluster. Hence, my main container will only start once init containers finish successfully stating yes, the service is available. Very powerful. You will see these in production all the time. Then there is a sidecar pattern. I want you to concentrate on one thing here. All these three are in a pink block and this is in a orange block. This is done deliberately to tell the distinction. What happens is, init containers, you define them specifically in your manifest file. So you will write init containers and then you will define init containers. But all these helper containers like sidecar pattern, ambassador pattern, adapter pattern, you won't write sidecar containers, you won't write ambassador containers, you won't write adapter containers. These are logical patterns, and the containers which adhere to these patterns are defined in the container block itself. And we'll see that in a little while, but I want you to know this at the beginning itself. Functionally, init containers and all these three patterns, they are quite different. So I wanted to throw that distinction at you at the beginning itself. And let's discuss what is a sidecar pattern. This is the most common pattern that you will see when I compare sidecar to ambassador and adapter. Extends or complements the functionality of the main primary container. That's fine. Use cases, logging, and here is the use case that we used here. Sidecar container can collect the logs and then deliver those logs to your central logging repository. Example, you could be using FluentD, FluentBit. All these can be examples of logging solutions that you can use. Second is monitoring, and we also saw this in our day 20 when we were using Prometheus. Prometheus can also run as a sidecar container, collecting all the monitoring data from your pods. Third is proxy, and you will see proxy mentioned in the ambassador pattern as well. Then I want to differentiate between what the proxy is when we talk about sidecar pattern and how they are different from ambassador. So let's define first what a proxy is. Proxy is, in my place, someone else is doing the job, or I do not want to disclose my identity, which is why I am asking someone else to do my job. That's simple definition of proxy, not Kubernetes specific, in general terms. Then when I talk about proxy for sidecar pattern, we are talking about service meshes. What are service meshes? A service mesh is an infrastructure layer that manages communication between microservices. You will see service meshes in bigger Kubernetes implementations when you have many microservices and you want those microservices to communicate with each other, because service mesh will provide things like traffic management. In traffic management, they can provide you with routing, load balancing, traffic shaping. Traffic shaping as in, maybe I do not want when microservice A talks to microservice B, it should not use more than 50 Mbps. That is something that we can achieve using traffic shaping. Then there is security, encryption. When microservices speak with each other, there is something called mutual TLS, MTLS. They can help with that. They can help with authentication, authorization, observability. Under observability, you have telemetry, distributed tracing, logging. So a service mesh can help you with all these things. And these service meshes, for example, Istio is one, AWS App Mesh is another. You can deploy them as sidecar pattern. The last one is data synchronization. Data synchronization, like I discussed here, file or directory creation, you can use them to continuously clone data. See, in init containers, this only worked for the very first time. Init container did its job, it cloned it, and then init containers vanished. And then the main container had that data. But what if you continuously want to sync some data? Maybe onto your pod or onto an external source. Then you would use a sidecar pattern, because init containers will go once they have done their job. They won't stay there. Like I mentioned, once init containers do their job, they go, and then the main container starts, and init containers just vanish. But when I talk about these containers stay with your pod. For example, if a data synchronization sidecar pattern is deployed, then that container will continue to run with the main container. And that's the important distinction between init and other three patterns. Init will go once the job is done, others will not. Varun, but what if the data synchronization container fails? If it fails, it fails. I'm not saying that these containers, part of these patterns, will not fail. They will fail. But what happens is your main application container will continue to work fine even if these containers fail. For example, if let's say my logging container failed here, then for some time my logging will not work because my log collector container is down, but my application will continue to work fine. And that is the beauty of separating things, of decoupling things. If monitoring container is down, then monitoring might not work, but my application will continue to run. So I hope you've understood the sidecar pattern. Now let's move to ambassador pattern. Container that acts as a proxy or intermediary between the main application and the external system. External system is the keyword here. So for example, if let's say my application pods want to speak with Amazon SQS or SNS or Azure's API gateway, then I will use ambassador pattern to do that. But Varun, why would you want to use a container to do that? Can't we have the main application do that? Again, I will take you back to the same concept. We want to decouple things. We want application to only do application things. I do not want my application to worry about authentication, authorization, or making DB connections. I will outsource those things. And when I outsource like external connections, making external connections to anything that's outside the Kubernetes cluster, that pattern is called ambassador pattern. It centralizes the logic required for external communication. So my container 2 here, which is helper, will only take care of external communication, decoupling these concerns from the application container. My main container only works on the application logic. So if it is a wishlist microservice, for example, it should only concentrate on creating or handling wishlist related things, nothing else. For anything else, I will have a helper container, and if that helper container is making outside connections as a proxy, then that pattern is called ambassador pattern. Now let's see the use cases, and here I also mentioned this, decoupling these concerns from the application container. Use case 1, API gateway, that is a request routing. If I am making connection to something outside to external world, then these patterns can help me do so. I'll have a container, and that secondary container could be Envoy. It's Envoy proxy is quite famous. You could be using that. Then the second use case is connection management. So when I am talking about databases, my application may want to connect to database 10 times in a minute. Then I do not want my main application to always open that connection, because that is an intensive process. It could be memory intensive, CPU intensive, or could be application code intensive. I do not want my application code to do these things. I only want my application code to run the application, nothing else. So you can use this to open and close external connections. Then retries. Maybe if my API is unreachable, the external API, then I want the helper container to do the retries. I don't want my application to do that. So in that case as well, you can use ambassador pattern. And last is SSL termination. If something connects to you, you do not want your application container to worry about SSL termination. And here your ambassador pattern container can help you with that. Then there is adapter pattern. This is the most simple one. Container that transforms or normalizes data between the main application container and an external system. What do you mean by that? Explain that in English. So if I go to day 20, you saw that we used a Prometheus adapter. And what was Prometheus adapter doing? Prometheus adapter was converting the metrics received from Prometheus server into a format that Kubernetes understand. Hence, Prometheus adapter is an adapter pattern container. So if Prometheus adapter was deployed as a container within the Prometheus server, that's a possibility, then this would have called an adapter pattern, because adapter pattern can help you with metric transformation or log normalization. Maybe the logs that I have received are in JSON format, but the destination for the logs only supports YAML. How do you do that? You can have an adapter pattern container perform log normalization for you. I hope all these patterns are clear now. Let me now scroll down and show you the manifest for each of them. You do not have to concentrate on what is happening inside, because we'll see that in a little while. For now, I want you to concentrate on, if I talk about init containers, you have a separate section for init container. I mention init containers, and then inside that we have a list. And why do we have a list? Because as I said, you can have multiple init containers and all of them run in sequence. Here I only have one init container, that is preparing the environment, and once this completes, then only the main container starts. This is just gibberish right now. This is just saying preparing the environment, sleep 10. So after 10 seconds, this init container will finish and then the main container will start. But in production, you will have actual use cases, and we'll see them in the demo section. And if I scroll down, you see that what is the init container doing and what is the main container doing. If I talk about Sidecar, then see, all these ambassador, adapter, all these are inside the containers block itself. But this one, init container, it has a separate block. And if I scroll down, I have a text as well. Init containers are functionally quite distinct compared to Sidecar, ambassador, and adapter containers, even though all are helper containers. These all are helper because in some way or another, they are helping my main application. Having said that, init containers will have a separate block, and once init containers have done their job, they will go away, they will vanish. And if they are gone, they won't take any resources, memory, CPU, anything else. They won't consume that because they are now gone. And these containers, they continue to use your resources. So as a best practice, we learned about requests and limits. You must define requests and limits for your helper containers as well. You can read what they are doing here. They are not doing anything much. I'm just saying sleep, sleep, sleep. So they are not doing anything per se, but you can use them for the use cases that we just discussed. And see, these are the use cases that I have personally used in my experience, but there could be many more use cases that you will see in production deployments where you are working. These are project specific. There are many possibilities. Maybe a Sidecar pattern is managing your certificates for you. Maybe the init containers are also downloading some secrets from somewhere and then utilizing those secrets in the main container. The possibilities are endless. So keep your mind open when you are learning these things. If you have something in mind, oh yeah, I can do this using this pattern, no? And these patterns are again logical abstractions because they will run as a helper container within the container block itself. And again, Sidecar is the most used, and ambassador and adapter you will still see. Now let's do one thing. Let's go to the demo now, the part that we all love. I will go to Visual Studio Code. What I have done is I have already created the YAMLs because we have been working with pod manifests for so long. I hope everyone understands them, and I did not want to waste time writing this because I will explain this to you line by line, but writing that live would have extended this lecture to a very long time. And now let's see what is happening. So we are creating a pod. The name of the pod is init pod. And then we have under the spec section, we have init containers. It's a plural. And then it is a list. So you can have multiple init containers. So we are naming this container check API and we are accessing a URL. So hence I have used curl images curl and the latest version for that. And then the command. So you see that I have written this command in this format. And let me do one more thing, view word wrap. And what I've done is I have also pasted a format that we have been using for a very long time here as well. So what we have usually done is we have used square brackets to specify a list, and that is what you usually do. However, when the commands get complex, when you use square brackets, it gets difficult to read. Hence, what I have done is I have used this format to display it. It is still a list. You see, command has, this is item 1 in the list, this is item 2, this is item 3. Here as well, this is a list. This was item 1, this was item 2, and then so on. If you are not following what I am saying, I would recommend you watch the YAML tutorial and you will understand these things. Then okay, let's get back to the topic. So if you want to see how you would represent the same thing in square brackets, you can refer this, but I'll for now comment it. You can find this in the GitHub repo. Okay. And again, always check out the GitHub repo because I have mentioned everything there. Whatever we are speaking is here. So if you want to revise it during your exams, your interviews, always go to the GitHub repo. This should be your one-stop shop for reading. If you want to get back to the videos, be my guest. But if you are a reading person, once you have watched the videos, then always get back to this repo. And I'll go back here. Okay. What we are doing is we are saying shell, then is the command sequences below. And here we are using a pipe symbol. Pipe symbol is a YAML multi-line block indicator. What this will do is you can write a single string in this format here, which will help in readability. So what we are doing is straight away my container will echo, my init container will echo, checking API availability. We are then saying sleep for 25 seconds. This was not needed. I added this because there is a next step. You will learn why. Then I'm saying until, there is an until loop. Then I'm saying curl kubernetes.io. So for this example, my main container will only start if kubernetes.io is up and running. And kubernetes.io is deployed onto highly available infrastructure. Hence, they have 99.9999999% of uptime. So this will always be up. Since this is always be up, hence I added a 25 seconds delay so that I can demonstrate to you how init containers function. Then whatever the output of this curl command is, I'm saying send that to dev null. Dev null is a black hole. I use this because I did not want my screen to be polluted with the output from kubernetes.io. Then I'm saying do echo waiting for API, and you will not see this because this will always be accessible. And this sleep 5 is only used if, for example, this fails. This is saying make the retry after 5 seconds, but this will pretty much always be accessible, and then we are closing the loop by using done. And once this is done, I should see echo API is accessible proceeding to main app container. Once we run this container, we'll first see checking API availability, and then after 25 seconds it will straight away go to this point and say API is accessible proceeding to main app container, and then our main app, which is Nginx, will start running. Again, I think I should do one more thing to make you understand this. I will create a new file. I'll name this test.yaml. So I'll write API version, and API version is for pod v1, and then I use kind is pod, and let's use this. Now I will remove this. So this is how we defined containers. Now for init containers, we are just adding a block, and that block is not under the containers section. It is a different block altogether. So here I'm adding init containers, and then they follow the same hierarchy as containers. So you will have a name of the init container, then you will have the image that init container will use, and then you will run the command whatever you want to use. The key thing is you define init containers, and then once they do their job, then only the main container will start. So let me just close this. So let's go to the terminal now and apply this. Okay, kubectl get pods. There is nothing running in this cluster. That is how I want it to be. Now let's do kubectl apply -f. I'm in day 2021 and we are doing the lecture for the same day. Kubectl apply -f init-c.yaml. I'll press enter, and it says init demo created. Now I'll write kubectl get pods. Interesting status. So we are creating one container in this pod. I want you to concentrate on this, okay? Here we have defined two containers. One of them is init, and then second is your main container. So we have defined two containers. However, this only says one. So the kubectl get pods command, the ready status column, is not even counting this as a container. And you will see that when we create two containers, this will have two, as in two containers. Out of two containers, two are ready. It will only have two then. Here our main app container has not yet started, which is why it is saying there is one container, that's the main app container, and it has not started yet. That's why you see a 0 here. Now before further delay, let me write kubectl logs, and the pod name is init demo, and the container I want to see the logs for is check API. Oh, so 25 seconds elapsed. So first it said checking API availability, and then it said API is accessible proceeding to main app container. And now if I run kubectl get pods, you will see there was one container, and that one container is running, and that one container is our main app container Nginx, and it only started once init container finished its job. I want to show this to you one more time, man. I was not satisfied. Too late to run that logs command. So kubectl delete -f init container. Yeah, I should use force delete as the process is still running. Kubectl delete pods init demo. I want this force is equal to true. I'm using this because it will first ask this container to stop the process, and it might take time at times. So I have used this, and you read this warning. Okay, now I will run kubectl apply -f and init-c.yaml. First I'll run kubectl get pods like before. You see init container in the status. Now I will run kubectl logs init demo, and the container I want to check the logs for is check API. I'm using tab completion often, so this is the pod name, and then this is the name of the container for which I want to check the logs. If I check this, it is now saying checking API availability. As soon as 25 seconds pass by, we should see that it now says API is accessible proceeding to main app container. And if I check the logs for my main app container, you should see Nginx logs. That is what we see. These are the Nginx logs when it starts. Okay. This one is fine, but I wanted to go a little more advanced so that you can see how multiple init containers will function. So let's go to Visual Studio Code, and I will open two init containers. This is the same, we have already discussed this. So here init containers, we have two init containers. This is the first one and this one is the second one. What is the second container doing? Now second container echo, this we understand, and then it is saying checking main app service availability. So first, as soon as you deploy this pod, you will see this message when you check the logs for this container, because at the very first line we are saying checking main app service availability. Then we are saying until ns lookup main app svc default svc.cluster.local. In this example, my pod will search for a service whose name is main app svc. So then we are saying echo waiting for service DNS resolution. Then the loop completes and it will echo service is reachable proceeding to main app container. The change I have done in my init container 1 is I have said that external API is accessible proceeding to next init containers. Now what I'll also do is I'll decrease this time to 15 seconds so that we do not have to wait for longer. And then let's go to the terminal and apply this. kubectl apply -f. I'll press enter. I'll run kubectl get pods. It says that my init demo 2 pod is created. It is still in the init container stage. You see, even though I have created 2 init containers, it still says 1 here, because it only counts the main container. I'll run kubectl logs init demo 2, and then the pod I want to check the logs for is check API. And no, it's still creating that container, is waiting to start, trying and failing to pull image. Why are you failing to pull image, dear? What is wrong? I'm using the curl image. That looks fine. Okay, let me check the logs again. kubectl get pods init image pull back kubectl describe pods init demo curl it has failed to pull and unpack image. Server misbehaving. Why is that? Let me run this again, because we just created a container using the same image. All this looks okay to me. kubectl delete pods. I'll delete the first pod as well. I'll delete the second pod as well. Why should I have added a force? Hold on. Let's run kubectl apply -f init. It says created kubectl get pods. Okay. 8 seconds. Error image pull. Again the same error. If I try to apply -f the first YAML, does it also give the error? kubectl logs init demo check API image to be pulled. Image can't be pulled. Bad request. This just worked. What's the problem? Okay guys, hey, the reason it did not work was because there was a problem with my internet connection. I was wondering, why did our first demo succeed and this failed, and we are using exactly the same image? And while googling, I found that my connection to the internet is down. Now let me run kubectl get pods. I will now apply that YAML kubectl apply -f, and that file is to, yes, it's created. kubectl get pods, and yes, kubectl logs init demo 2, and we are checking the logs for check API container, and it's saying checking external API availability. So my connection to the internet is up. I'll go to Visual Studio Code, and that is what I expect, checking external API availability, and after 15 seconds it should say going to the next container. External API is accessible, proceeding to next init container. And our next init container is ensuring that this service must exist, and it will try to ns lookup this service every 5 seconds, but because that is what the retry logic that we have defined. Every 5 seconds you check for that. And if I go here now and check the logs for check svc container, and that is what I have named this container, check svc, then the logs will say it is not able to resolve this because this service does not exist in my cluster. If it does not exist, this init container will not succeed until it finds this service. And if this won't succeed, my main container will never ever start. So it must must complete. Both these should successfully complete. All the init containers must successfully complete for your main app to start. Now let's go here. I have a service YAML. It's a normal cluster IP service that I'm creating, and I'm calling this service main app SVC, which is what my init container expects. So I'll go here, I'll run kubectl apply -f, and the name of that YAML is svc.yaml, if I'm not wrong. Yeah, svc.yaml, and here is my configuration. So I'll press enter. It says the service created. Now let's check the log. It's still saying waiting for DNS resolution because this is performed every 5 seconds. So 3, 4, 5. Okay, give it some time. Service is just created. Service is reachable. Proceeding to main container, and it resolved. The IP address that was assigned to this service was 1096.135.170. I hope this is clear now. Now, if you are wondering, because if you see something on screen, you start to ask questions, why is the DNS this? So I quickly want to show you that as well. If I run kubectl get svc-n kube system, then you would see that I have to spell it correctly. And if I run this, I see the kube DNS. There is a service created whose name is kube DNS, and that service has an IP of 1096.0.10, which is why every DNS resolution in Kubernetes cluster will go to your kube DNS. That is this IP, and this is this IP. And if I run kubectl get pods, you see that there are 2 core DNS pods, and this service, that kube DNS service, is load balancing the requests between these 2 pods. If you have any further questions, just park them in your mind somewhere, because we are going to discuss this in the DNS section of this course. So if I now run kubectl get pods, I see that my main container is now running because I see 1 on 1. Perfect. I hope this gave you production like idea of how things happen. Let's do a demo for Sidecar container as well. What I have done is I have created a YAML already, and it is a very simple YAML. What we are saying is, and the important distinction is, both these containers are defined within the container block itself. There is no separate block for any of these patterns, sidecar, adapter, or ambassador. So the first container is the main app container, and it is Nginx latest, port is this, and then the container port is this. Then we have a sidecar container, and then the sidecar container name is health logger, because this is logging the health for my main container. We are again using the curl image. The command that we are running is sh-c. Then we have a YAML multi-level block indicator, and we are running a while loop here, which says while to do curl, you have to curl this thing, that is localhost 80, and y container 2, that is the helper container, able to curl port 80 on localhost because network namespaces are shared. And we are sending the output to dev null, and we are saying and echo main app is healthy, and implies run this command only if this succeed. If the first command succeed, then only run this. And then we have a or, which is denoted by 2 pipe symbols, which says echo main app is healthy. Now or says if the first command fails, which is this one, then run echo main app is unhealthy. And we know it will run that because if we kill container 1, this container here, the Nginx container, then this will not work, and we will see this main app is unhealthy. So first, let's do one thing. Let's create this sidecar logging demo pod. I'll go to my terminal. I'll run kubectl apply -f sidecar.yaml. I'll press enter. It says sidecar logging demo created. I'll run kubectl get pods. I'm creating 2 containers here, okay, and I see 2 here. Important distinction, init containers were never mentioned here, but sidecar, ambassador, adapter patterns will be mentioned here. So it says there are 2 containers, and both these containers are being created. If I run kubectl get pods, error image pull. Is there something wrong with my connection again? Don't do this, man. Kubectl describe pods. I want to describe the sidecar. And I believe it's the same thing now. It's with Nginx. What's wrong with my internet connection today? Please pardon me for this. I mean, you should not have been through this. The connection is working now. So I'll again run kubectl apply -f sidecar -. I'll now run kubectl get pods. It says container creating. It says running. Just don't leave it here. I have an important concept to show. So I'll now run kubectl exec. Now what I want to do is, if I check logs of this, kubectl logs sidecar, and then I want to check the logs for health logger, and health logger will every 5 seconds display main app is healthy, which we understand because that is what we have defined in the YAML. We are saying main app is healthy, echo this, and since we are running this every 5 seconds, it will display main app is healthy every 5 seconds. So again, if I run this again, you will see that there are few more entries now. So now let's do one thing. I want to kill the main container so that I can see this main app is unhealthy displayed. So for that, let's do one thing. I will run kubectl exec -it to get integrated terminal. Exec is to log in into the container or to run commands into a container. Then I will run the pod name is sidecar logging, and the container I want to exec into is the main container. Is it called main app? Sidecar demo logging main. I should have added a -c. Is that what it is? Yeah, the reason it was troubling me. And I'll write hyphens, and then I'll write bin sh. I want to log in into the container. I have logged in. Now I'll run kill one. It said the command terminated, and you see that I am thrown out of the container because I killed the container essentially. But if I run kubectl get pods, it says running and 2 of 2 are ready. I just killed the container. What is happening? I want you to concentrate on one thing. When I run the command here, kubectl get pods, the restarts were 0. But here, oh my god, restart is 1. Why is this? What is happening? I killed a container, but the kubelet automatically restarted it. Why did it do so? That's the default behavior of kubelet. When you create a deployment, when you create a pod, that's the default behavior. Whenever a container gets killed or the container fails for XYZ reasons, then the kubelet restarts it. And why does it do so? Let's check the YAML for this pod. kubectl get pods. The name of the pod is sidecar logging. I'll add -o YAML because I want the output of this command in YAML format. I'll press enter, and if I scroll up, I should see something called restart policy. Restart policy, and the restart policy is set to always, which is why this container got restarted. So let me just quickly copy this. I will go to my Visual Studio Code. I will go to the sidecar containers, and here under the spec section, I will mention, I'll indent it properly. I'll paste this. Instead of always, I will write never here. I'll save this file. I'll go to my terminal. I will kubectl delete pods sidecar. I'll add a force flag here. I'll press enter. I will again apply kubectl apply -f sidecar. Press enter. I'll now run kubectl get pods. This is working. I'll now run kubectl get pods again. This will run. Now I want to kill the container once they are ready. So let's wait for this to be ready. Man, I hope the internet problem has not stricken again. I'll run this once the connection is back. Container creating. I'll add -w. -w is watch. So whenever this status changes, it will display this on the screen itself. It's now running. Okay, now I'll run kubectl. Again, the same command that we used to kubectl exec -it, and then I will write the pod's name, and pod's name is this -c to mention the container name. I want to go inside main app, and then I want to run bin sh. If I was running kill directly from here, it was not working for some reason. I'll press enter. Then then here I'll run kill one. This will kill the main process. If I now run kubectl get pods, not ready. Out of 2 containers, only 1 is ready. The status has changed to not ready. Restart did not happen because we used a policy called restart never. And then I will now run kubectl logs, and I want to check the logs of Sidecar logging demo, and then I want to check the logs of health logger container, and you see main app is unhealthy. That's all for day 21. I hope you have a good understanding of multi-container pods now. I would again like to apologize for the internet connection issue that happened during our demos. In the next lecture, we will cover health probes to ensure your apps stay healthy and resilient. If you have any questions, feel free to ask them in the comment section and I will reply. If this helped, do consider liking, sharing and subscribing. It will mean a lot to me. Thank you very much.